In fact, I retired 3 years ago from a company. I was at a company. Now I'm at MIT. And there is just so much to learn. And it's so interesting that I feel like a teenager again. So you're lucky to have so much possibility to learn in front of you.
Probably you'll have to give people maybe 5 minutes more, not more.
You tell me. So you gentlemen that just came in, everybody before you said who they are and what they do. So why don't you tell me what you do?
I'm a student.
You're a student? In what topic?
My topic is understanding the natural text processing.
Natural text processing. Also, so another colleague back there. So, and you in the black sweater?
I'm a PhD student
In?
Moskovской technical university. I'm doing natural language text processing
Also.
as well.
Uh-huh. And what languages? Russian?
You mean natural languages? Yeah, Russian.
English?
English, because
Of course.
most
The text
everything everybody's doing
is in
so,
English, right?
Work on English and try to adapt for Russian.
Uh-huh. And you?
Moscow State Technical University, NLP.
NLP. Okay, everybody does NLP. You know, NLP was not very successful. Natural language processing was not really successful until maybe 10 years ago. And now with really powerful computers and massive databases, all of a sudden it's a superstar. So it's a good topic.
We are online.
We're online, all right. And you're saving it also, is that true? Storing it to put online later? Meaning it's live or?
It's live translation. YouTube will record itself.
Oh, it records itself.
It will remain in YouTube.
Oh, okay. I guess that's a good thing. So, Sergey, whenever you'd like to start.
Yeah. Maybe 3 more minutes.
All right.
We promised to start translation at 4:30.
Oh, I see.
So
I see. And the translation is done by somebody remotely?
I think
Hello?
the watch is will understand you.
No, but the translation, where does the translation occur?
I don't even translation.
Recording.
Yeah.
You mean recording? I see.
I mean translation via the internet.
Yeah.
Language translation.
Right. So this gentleman I met last week, so he doesn't have to report in. Aha, 2 more people have to report in. So the 2 people that just came in the room, everybody so far has said what they do. So I'd like to know what you do as a background, so when I'm talking, I know who I'm talking to. So what do you study?
Hey everyone, my name is Nikolai. I work as a lead data scientist.
A data scientist?
Yeah.
Wow, great.
In a company here in Moscow. It's called Mail.ru Group, and Xenia is a data scientist in my organization.
Really? So what subjects do you do analysis on?
We do mostly online advertising.
I see. So you're looking for advertising trends and customer analysis and so forth.
We are doing audience segmentation mostly.
Uh-huh.
So we search for different segments like types of income, types of
Sure.
education, everything like that.
Uh-huh. Good. All right. So I'm going to say some things here that I suspect are going to be new to you. Welcome. 11 people, okay. Not 11,000? So one basic difference, really big difference, is probably how I define data science and how you define data science. So I'm a scientist, and I do theory, and I'm working with scientists at IBM and Stanford and Berkeley, and we're looking for the underlying principles that help determine how you do data analytics, and to prove correctness to a degree, estimate correctness, likelihood, probabilities. Most people say that data science is just doing the analysis, but I'm one level up.
Yeah, but we call ourselves data scientists just because it's a nice word, buzzword.
Everybody does. I give lectures all over the world to data scientists. Well, I'll try it up here. I'm going to start the way I normally start. Shall we start now, or? Okay.
Okay. Dear colleagues, I welcome you to our seminar, of our 180th seminar of Moscow ACM SIGMOD chapter. Today we have a distinguished guest, Michael Brody, from Massachusetts Institute of Technology, actually Michael was invited as a keynote speaker for the RCDL Dundee conference, and it was a great opportunity for us to invite him to give a talk on our seminar. And Michael also asked me not to spend a lot of time for the introduction of him, so just a couple of points. For 20 years he was a chief scientist of IT in the company called Verizon. This year, this company holds 15th rank in Fortune 500. And now he's a professor and research scientist at the Computer Science and Artificial Intelligence Laboratory, Massachusetts Institute of Technology. So we kindly ask Michael to share his 40 years experience in
40 years.
different fields of computer science, big data, data science, and so on, and give us his vision of this important field. So, Michael, the floor is yours.
Thank you, Sergey. It's really a pleasure for me to talk with you, and I'd like to talk so you can understand me. So if I talk too fast, either with English or with the ideas, please tell me. And if you have a question at all, I'd love to hear it. Because my objective is not to give a lecture, but when you walk out that door, you have at least one new idea or problem. So that's my purpose is not to give a lecture, but to share information. So data science is obviously very popular. In fact, it's one of the most popular topics in computer science. So when I retired from Verizon, which is about the 15th largest company in the world, and that was only 3 years ago, they didn't use big data. Everybody is using big data, but one of the biggest companies in the world isn't. I thought, that's odd. And then I found out everybody talks about it, but very few people do it. So I wanted to understand what big data was, or what data science was. So I call it data analytics. So the questions I'm trying to answer are, what is big data analytics? And so the data scientist at the back of the room, the thing that I am trying, this is the one idea I'd like you to all have in mind when you leave, that you may not have now, and that is data science is a completely new way of thinking. It's not just data analysis with more data at all. It is a completely new paradigm, a new way of thinking. So I'd like to convince you of that, because when you see that it's a new idea, you need new mathematics, you need new ideas about how to do problem solving, and when you have the new idea, let's say you discover algebra, all of a sudden many problems are easier because algebra solves problems. Data science, I think, is the same. It's hard to understand as a simple extension of just using Excel. It's much, much more than Excel. I'm a data person. My background is in databases, so my interest is not, I'm not a statistician, I am not a geneticist or a biologist or a marketing person. I don't understand those domains, I understand data. But I'm going to give you an example in a minute that will tell you that if you are a data expert, you also have to know something about the way the data is going to be used. So what is the role of data in data science? And the question I like to ask is, this is really easy stuff, right? What could possibly go wrong? Well, I want to convince you that things could go wrong in a very serious way. And that's why we need to understand how to estimate the correctness of the results of the data analysis that people use in big data. So I'm going to give my own definition of data science, but I'm going to use the lecture to build up to the idea. So I'll give the definition almost at the end. If I gave it now, it would be hard to understand. When I give it at the end, because of the examples, it'll be easier to understand. Okay, so I'm going to give you an example of a data scientist working together with a database person. So let's say this is genetics, and the person is doing medical analysis in genetics. He or she has a PhD in medicine and genetics and wants to study a particular topic. And they say to the database person, go get me the data so that I can do my analysis. So this is what the database person goes and does. Discovers data sources that are relevant to the question. All data is dirty. You have to clean it, and it's called curation. Like one curates art, but you have to curate data to understand what it is and integrate the data together. So for example, when you travel on the metro here, you get many pings go out through Wi-Fi about where you are. So let's say you travel from here home, and there may be 1,000 pings saying that it is Dimitri. So you've got to make sure when you get 1,000 pings, they're all Dimitri. And for you, all the pings about you, is you have to consolidate it that it's all you. They're not 1,000 random people, they're Dimitri. So it's called data deduplication, data integration. It's a very hard job. And then the data person says, I analyzed all the data, and I have a lot of metadata about the properties of the data set to help you understand the data. So now it's ready for analysis. So the geneticist says, you're fired. Because the data person made a very big mistake. Now, does this seem unusual to you? Does this seem it's hard to understand? Yeah? This should be hard to understand. Oh, I shouldn't go over here? Sorry. Well, maybe I'll come back here so they won't be in front of the screen. So this is something that I knew a little bit about. It has to do with statistics. And I'll give you an example later. When you have a data set and you're going to do an analysis over a data set, you say, I have a hypothesis. Does A imply B? And if I evaluate A implies B over that data set, I have an impact on any other hypothesis that is evaluated later. It's called data reuse. So let's say my next hypothesis is B implies C. If I evaluated does B imply C, the guarantees on the error bounds that I would get would be different if I ran it alone instead of running it after. So this person analyzed the data set. He looked at the data set from many, many points of view to understand the metadata. You don't do that in science. It negatively impacts the statistical outcomes. So why did I, I gave this talk at a conference, and two people with PhDs in data came up to me after the conference and said, I don't understand, why did this happen? So this is, I would say in marketing, this may not apply because the error bounds and the impact of a negative result in marketing or retail or process analysis may not be very significant. But in science, in genetics, in particle physics, in other areas, it does matter. So if it's movie recommendations and you make a mistake, you turn the movie off. Netflix recommended a movie. After 10 minutes, I thought it was awful, so I turned it off. The impact is nothing. But if I give you a drug because the data analysis said you should have this drug, and then you die. So you understand there are different kinds of decisions. Error bounds mean different things in different contexts. Okay, so I wanted to prepare you that data analysis is not simple and it's not easy. And if you read things in the press, it sounds like everybody's doing it and it's very easy. In fact, this is a marketing chart. This is about a year old, and it predicts the growth of the big data business. So it doesn't matter what the chart says other than this is going to be bigger and bigger and bigger every year, right out to 2026. It's just going to keep growing. And pretty much everybody knows the Gartner hype chart. So the 2014 hype chart had big data on it and data science. So data science was becoming popular and big data was just past being popular. This year, it doesn't even show. They're gone. There's a good reason for some of this, but it shows that big data and data analytics is trendy. That means people think it's important, and I'm going to tell you that it is extremely important, and the people they survey for this don't know much. Like the internet boom and the dot-com crash, everybody thought the internet was going to be big and the stock market went up and then it crashed in 2000. I mean, with respect to internet stocks. That didn't indicate the importance of the internet has changed our lives. I am now lecturing on the internet. Before 2000, you could never do that. And so it's not someone in Russia could see this, someone in Thailand can see this. It's changing our world. So big data is the same. It's going to change our world in a very big way. Oh, machine learning is on there now, so that's new. So big data, there are lots of products. I think it's important because there's a scientist, a colleague of mine, who called this the fourth paradigm. I'll explain more about that in a moment, meaning it's a new way of doing science, it's a new way of doing analysis, and I'll talk more about that in a bit. It definitely accelerates the speed with which you can find a scientific answer. We have clear demonstrations of this. I will mention one or two. I'll go and give you some more examples. I am happy to say that I've provided some advice to the White House in the United States concerning big data in medicine. And not just the White House, but 45 governments around the world say that big data and data analytics is the policy of the government. The government says they should be doing it because it's effective and it's much cheaper than the alternative. And I'll tell you what the alternatives are. And if you read the literature or you read the newspaper, it looks like everybody is doing it. Computational biology, computational chemistry, computational astrophysics, everything is using big data. But in actual fact, people are not really applying it anywhere near as much as they talk about it. Gartner says that even for the next 2 years, 60% of all projects will fail. And I think that means how to use it and the tools to use it it's very hard to apply this really effectively. The study by EMC says 60% of companies are putting it into practice, but only 20% are making any significant change as a result, but only 1% are doing the magic you hear about, making $1 billion, discovering cancer, discovering the Higgs boson. That's a very, very small percentage. And that's where I think the great value is. So that 1% has got to go up. Well, we have to understand data science to do it. So I imagine that you're doing, the people at the back of the room are doing customer segmentation, right? So customer segmentation is looking at data and looking at something people know really well. Customer segmentation has been something that's gone on for 20 or 30 years. Big data, the greatest value of big data is not looking retrospectively in the past or improving the efficiency of something we're doing now. It is looking forward and finding things you never discovered. I'll give you an example of that later. The thing I want to emphasize is data science and data analytics is in its infancy. We're just beginning to understand it. I'll give you a little bit of history about that in a moment. So this has to do with medicine in the United States. The White House and the National Institutes of Health have identified data science as a means to provide patient care for the right person at the right time. Yes, for the right person at the right time. That means I don't say for all people of a certain age and with these characteristics, you should probably take aspirin and then later do something else. You say for you, with your characteristics and the problem you're having right now, here is the treatment I recommend. And I know, I'm confident that it's going to work because I've already found 30,000 people who had the same situation and this treatment worked for them. You see what I mean? You look in the history and you say, this particular person has this specific situation at the moment. Has that ever happened before? And what treatment was very effective? So there are 4 diseases listed here. Each one costs America, just for people 65 years and older, $150 to $200 billion a year. That's traditional methods. It is very likely that big data analytics and personalized medicine could reduce this at least in half. So I don't want to emphasize the wrong thing. The most you want out of a data analysis is the correct answer. What is the right treatment for Dimitri? That's what you want. You also want it faster and more precise. all of these drugs, but just this one. And you want to find out the solution very quickly. If I talk about money, it sounds like the government is trying to save money. That's true, but more importantly is improving the quality of life of patients. Okay, so what could go wrong? I'm sure you've seen these charts on the web. They're called correlations. And this says the amount of chicken consumed corresponds directly to imports of crude oil. So what this is saying is there are many things that correlate, but there is no meaning in it whatsoever. So how do you distinguish between a correlation and something that happens out there in the real world? So that's the science that I'm interested in pursuing. Google Flu Trends, has anybody heard of Google Flu Trends? So Google Flu Trends was looking at Google searches, and people would say, where do I find a cold remedy near me? Or how do I cure a cold? Or what's a good cure for a headache and a fever and so forth? And they'd look at these queries, and they would predict that there was a breakout of flu in a certain geographical location, and that it was traveling by looking at the queries that people made in Google searches. So that was a really cool idea. It worked for about 6 weeks. It was wrong 100 weeks out of 108. So these things are correlated, the queries about flu and cold, but it wasn't precise. So how bad could it get? There's an organization, it's actually in Cambridge, Massachusetts, but it's an international organization called the Future of Life. And very famous people are members of it: Bill Gates, Stephen Hawking, Elon Musk. And if you go to their website, you'll see every famous AI professor in the world. These people saying they want to mitigate the existential risks facing humanity from artificial intelligence, from computing. Will super intelligent computers become an existential threat to humanity? So these guys are concerned that using computers incorrectly, or computers will get some spirit of their own. So there are very serious concerns that there's a negative side to using data analytics incorrectly. On the other side, how do you take responsibility for the decisions you make with data analytics? And out of the legal community in the United States is this term called algorithmic accountability, which says, let's say a machine makes a decision, like it gives you a job, but it doesn't give you a job, because the computer is used to select candidates for jobs. What happens if the algorithm is biased? So how do you determine that a computer was used appropriately? The algorithms are used to make reasonable decisions that correspond to the law. So how do we know that an outcome is correct, it's complete, that is, it answers as much of the question as possible, and that it's efficient? Well, at MIT, we have been working with Mount Sinai Hospital in New York City and have produced, out of big data or data analytics from clinical care, results in curing critical liver disease. That is, being able to predict under what conditions a patient might be close to dying based on their past history and other people like them. And the results are very confident. That is, the results are proven statistically. The hospital won't use it because they don't want a black box. They don't say that this machine tells you, oh, watch out for this thing. I want to know why. So understanding what happens is different than understanding why it happens. And the hospital wants to understand why it happens. They don't trust the machine. I'll come back to that in a moment. So we live in a world that is driven by computer decisions, and big data is being used in almost every human endeavor. And we want to make sure that when we make these decisions with the computer, the decisions correspond to real problems in the real world. So, I'll be a little bit more philosophical. We think that we're looking for truth, but I hope you realize there's no such thing as truth. Truth is relative to a set of rules. Let's say truth in medicine is whether you get better. The truth in a cure is that someone gets better as a result of taking the cure. Or the truth in particle physics would be you found the Higgs boson because it was there. So, but science produces evidence-based causality. That's what the scientific method has done for about 400 years. The best we can do in data analytics is evidence-based correlations. So you remember the correlation between, was it chicken and oil? It's really correlated. You can prove it's correlated, but it means nothing. So how do you go beyond correlations to what you say in science is causation? That is that A literally implies B. That is, smoking cigarettes causes cancer, for example. So that's what we want to do. So the history of science has been, you have a hypothesis, and you create an experiment to test the hypothesis, and you look at the data to determine if the hypothesis is true or not. The reason data analytics with big data is a paradigm shift is we go the exact opposite way. We don't have hypotheses. Sometimes you do, but the extreme case is you have no hypotheses. Where do the hypotheses come from? Can anybody tell me? No, you're talking about humans. We're talking about data analysis here. So experience is what humans have. Oh, if by experience you mean in the data, and the computer finds patterns in the data. So the answer is the computer looks for correlations and estimates a high probability that they're true. That's called hypothesis generation. So hypotheses used to come from people to look at data. So wait a minute, let's just look at the data and see if there is any correlations that look like they might be real. And then the larger way to go is you have many hypotheses which becomes a model. For example, the standard model of physics has many, many, many hypotheses in it, and you go and verify individual hypotheses at CERN, the accelerator in Switzerland. So now, can we look at CERN data, the data from the linear accelerator, and determine hypotheses from that? So data science does go this way. That is, I can have a hypothesis and ask a very large database, is this true? Does it seem true? But a more powerful way is to have the machine go that way. So I'm going to... Okay, so it seems that data analytics or big data is brand new. And I want to tell you that it's not. It's very, very old. Some things have changed. That's why it's a paradigm shift. So mathematics goes back 4,000 years. Statistics has been around actually before Christ. But the data science techniques from statistics that are being used today were actually defined by George Box, a statistician in 1976. Of course, George Box could not understand the data we would have today. But his rules are some of the best rules we have. We don't have new rules yet. That's what I'm going to search for. The scientific method goes back a very long way. And Jim Gray described the fourth paradigm in scientific and engineering discovery. How does a scientist discover something? How does an engineer discover something? We go back and start theoretically. Aristotle wanted to look objectively at natural phenomena. So how can you objectively determine cosmology, where the planets are, or how the wind goes, or how water falls, or something like that? And then came along with the Bacons the experimental method, and we started experimentation, and that was the big breakthrough in scientific development. Then with computers, we came to simulation, and we would do experiments in the computer and not necessarily in the physical world. We would do a bit of both, but that was called simulation. We are now at the fourth generation, or the fourth paradigm, and that is something completely different than these. These three started with a human saying, hey, I wonder if this is true. Create an experiment and determine if the data says it's true or not. This one goes that way very, very well. That is, using more data, the same techniques, but using more data. But the surprising one is coming the other way. That is, now the example I use is economics. And you know, around the world at the moment we have, oh, look at that sunset. It's so pretty. Around the world at the moment we have a migration problem. People are going from Syria into Europe. Mexicans are going from Mexico into United States. And in Europe and in United States, we have conservatives who say, stop having these people come in because our economy is going to fail. And the liberals say, bring the migrants in because we need them for our economy will improve. So some say the economy will go down, the others say the economy will go up. But of course, we don't know what their models are. Why don't we go and look at the history of data and see whether migrations cause the economies to rise or to fall, and not have politicians say stuff that is not provable. So I would argue that data may provide a better form of analysis that is less biased than humans saying, oh, if we let the migrants in, we'll all be out of work because they're all going to do work for lower salaries. So why don't we look at the data and see what actually has happened in the past or what might happen in the future? So the scientific method and the mathematics are about 2,000 to 4,000 years of history, and we know how those work. Computers have only been around 60 years or so. E-science was declared around 2000, and Jim Gray and some others declared big data around 2007. And they've been used, the results have come out, very positive results have come out of drug discovery. Cancer drugs have come out of using big data. The Higgs boson was discovered using big data. Well, experiments and big data. I'm going to give you an example. And this has only been 15 years. So I'm saying this is a new paradigm. It's a new way to do science and discovery. But it's brand new. So we don't have the theory or the understanding of it. There's something I didn't say up here. Data-intensive analysis of everything. The scientific method and engineering used to be the basis in which we would do the scientific method. We would use the scientific method to evaluate a scientific or an engineering hypothesis. But if you look at big data, they're using it in social studies, they're using it in humanities. A very effective area in which big data is used is in natural language translation and natural language understanding. It's extremely powerful. In fact, big data is more effective in translation than human beings, so in terms of scale. So it's new. The paradigm of big data is new. They always take long developments for getting the concepts, the theories, and the procedural aspect of how you do it. So I'm simply going to claim it's brand new compared to the scientific method, so we're only just beginning to understand it. So I'm now going to give you an example of how big data is changing scientific, in this case, medical discovery. If you're looking for solutions in cancer, comes from the Cancer Commons. This is the cancer community. You take a biopsy, you take some skin that you think is cancerous. You put it in an Illumina machine, you sequence it to see the genes, and then you analyze the patient's DNA and RNA compared to normal DNA and RNA, and you look for what are called anomalies that are variations from the norm. So you think that might be a cancer. So you find a cancerous cell which becomes the target for, let's say, rays. You're going to use some sort of rays to kill the cancerous cells. So you do some sort of test to make sure that the rays aren't going to kill the person. And then you start treating the person with some sort of radiation called or chemotherapy. That could be the result as well. You monitor the patient to see if these anomalous cells, these cancerous cells, are dying, and you either win or you lose. It might work, it might not work. You may have found the cancerous cells, you may not. So this is the sequence you go through. And typically this sequence, to find a solution, whether it's chemotherapy or rays or a drug, tends to take 10 years and about $10 billion. So it's a very expensive way to do it. Now I'm going to try to transfer this into the big data side. This is data, and this is empiricism. This is the empirical side. So it looks like this. On this side, where you have a model of the cancer and you have data, it's called what? I want to see what happens. Oh, I found an anomalous cell. I don't know why it's anomalous, but I know that it's not normal. So you only know that it happened. That's the data part. Over on this side, you want to discover, why is this cell cancerous and this one isn't? What are the conditions that led to this being cancerous? Because if I can find out, I can go and stop the reasons that cause the cancer. That's why you want to find out over here what that is. So the way we do it conventionally is a human produces a hypothesis. The hypothesis with the data says, I think there's a correlation. I think this is a cancerous cell, and I think you can cure it with this chemical or this drug. You run an experiment using that drug on that cell, and you get a result out, and you say, over 500 patients using this drug, that cancerous cell was stopped from being cancerous with an error rate of 0.05 and a probability of 97%. So any outcome in science is probabilistic. So this is conventional science. It uses data together with experimentation. The two go together always. All right, now I'm going to tell you that there's been a shift in the thinking from empiricism to data. So we have a new way of thinking. In the old way, we used small amounts of data, and now we're using massive amounts of data. So that's everybody knows that change. You go from using spreadsheets of data to using massive databases. So that's obvious, right? But the next one is really interesting. You shift the resources from science and empiricism that discovers why. That, by the way, takes 10 years. And we go over to use data to analyze the data to see if we can find a pattern. So I'll just give you an example. And this comes from the IBM Research Lab in Almaden in California. And I was visiting there last week. The normal discovery of an anomalous cancerous cell they find about one new type. It's called a kinesis. They find one new one per year. The entire field, all the scientists working together, they normally produce one in 1 year, and then they take 10 years to develop the drug. So that's the normal method. The IBM lab, together with Baylor Medical Institute in Texas, decided to look in published papers that had done analysis of kinases. And once their data experiment was set up, this is all done in data, no people involved at all, just looking at data. Through textual analysis of published papers. That's what they were looking at. They found 9 in 2 weeks. Isn't that cool? So the question is, how do you know that those 9 were real or not some correlation? So here's the trick they played. They did the textual analysis until the year 2003. That's when they found the 9. So based on when they started to 2003, by the way, the community knows about 257 of these things. What you want to do is discover a new one. So in the 10-year period they analyzed, they found 9 new ones. They then looked at the literature from 2003 to 2013, and 7 of the 9 had been proven in the laboratory to be real. This meant that the 2 remaining were highly likely to be also true. You see? So they discovered the pattern. They found 9. Okay, these 9 look like they're real, but how do we know whether they're real? Well, 7 of them have already been proven. Oh, if 7 of them have already been proven, then these other 2 are highly likely. Now those two kinases are in drug development, and they believe, and so the speed up was 1 kinases in 12 months, and they found 2 in 3 weeks. It was 3 or 4 weeks, let's say 4 weeks. So that's an acceleration. So I'm telling you that you can look in the data to find information you otherwise wouldn't find. They analyzed 70,000 papers. For a doctor, an oncologist, to read the 70,000 papers would take a lifetime. They estimated 38 years without sleeping, but you have to sleep. But that's one person, and that person wouldn't be able to share the knowledge. Watson, the machine, the IBM discovery machine, actually analyzed and annotated those documents and now made that information available to doctors so they can query the entire corpus of published papers on kinases for P53, a particular protein or enzyme. I took a long time to tell that story, but it's so exciting. And I'll skip slides in the future that relate to that story. So another change is we move from being theory-based or strategic, saying, I think we ought to look at P53 as a direction to find a cancer cure, to being tactical. We say, hey machine, what kinases are the ones we should be looking at? The machine finds correlations and it suggests them to you. So you go from being strategic, I think I'm going to do this, to being tactical and say, what does the data say? That's a huge change. You can say it another way. It's theory-driven or top-down versus data-driven or bottom-up. Those 2 lines mean the same thing. So in the old way, you would say, I think this particular kinases is a potential cancer cure, and you go and study it. Okay, that wasn't it. By the way, there are 5,000 kinases. So, and 257 are known. That leaves another 4,500 to analyze. But rather than analyze everyone in a separate experiment, you may be able to use the data to tell you which of the remaining 4,500 are worthy of looking at. So I said at the beginning to some of you at the back about textual analysis that it's much more successful now than it was a decade ago. And the reason is the amount of data and computing power that's available. And so science has led to e-science, and accelerating scientific discovery, I just gave you an example, is because of computing power and better algorithms than we ever had before, and a massive amounts of data. So where is it being applied? I've been studying big use cases in big data for 3 years now, and I find they have been applied in every area of human endeavor. Okay, so now I'm going to go on. Any questions or comments? No? Don't hesitate to ask. So now I'm going to go on and tell you carry on with this diagram. This is where we left off, where a human would have a hypothesis. You build a model. You use data to look at correlations that seem reasonable. And then the experimenter says, oh, you're crazy. That one doesn't work. Oh, that one looks like it might work. That one might work. And then you invest resources in a real experiment. You go through the experiment and you get some results out. And then you're done. So that was the typical cycle. What happens with big data is you actually say to the machine, what correlations look reasonable? Okay, so this has another explanation. In about the 1960s, there was a paper in psychology that claimed that the human mind can think of, it's called in the active mind, the mind that's currently thinking, as opposed to memory. The mind that's currently thinking can think of 7 plus or minus 2 ideas at any one time. So if you want to think of something new, you probably can't think of any more than 5 or 6 or 7 things at a time. So human beings are limited in how much they can understand at any one time. Deep learning algorithms, do you know how many variables deep learning algorithms look at? Whether it's textual analysis or image analysis? Billions. So a computer can look at billions of things. So that's where acceleration comes from. Rather than a human saying, oh, you know, here's an idea. My son is doing a PhD in biology. He's doing it on 2 variables. If you use a machine, you can say, go look at 1 billion things and just tell me the top 1,000. I haven't got time to look at the rest. What does the top 1,000 mean? The top 1,000 means if you find 1 billion correlations, I want you to rank them in the likelihood that they're really going to be true when I test it in the real world. That's where we don't know how to do that very well yet. Okay, so what happens in big data is, let's forget that you did this and you just have some ideas, probabilistic ideas. Oh, no. This is a circle. You can start anywhere on the circle. Let's say the machine comes up with 1 billion hypotheses and ranks them based on probability that they're meaningful, and you have the humans decide, oh, this is the act. I'll just finish this. So in the Watson example, the machine came up with thousands and thousands of alternatives. And the humans looked at it and said, you know, the 9 didn't come out of the machine. Thousands came out of the machine. And the humans were working with the machine and probability to determine which are more likely than others. That's how they got down to the 9. So the machine on its own didn't come up with 9. So it's machine driven and human guided. And you put a small number into the model and you rapidly iterate. So if you're using machine learning algorithms, you iterate extremely fast until you converge on something that looks like it's real. You then feed it over here, give it to these guys, and something that is new in medicine and in science, it's called adaptive adaptive clinical trials. So let's say we start a clinical trial with, let's say, 4 segments. You partition the patients into 4 groups, and you have different treatments. You start the experiment, and you watch the direction that is being achieved in each group. And 2 of the groups look like they're diverging. That is, whatever the hypothesis was not working for them. But the other 2 groups was converging. So you say, oh, let's stop the experiment right now, throw those 2 groups away, or the hypothesis for those groups, refine the hypothesis. So the hypothesis comes up here and it says, this hypothesis is more refined because we think it works for these 2 groups. But scientists, give me a model, simulate this and see how it works on big data. So you take the 2 groups and you look to see, is there evidence that this group or this group improves? And so that's the way you accelerate through here. So you get lots of ideas, you test them out, some of them work, some of them don't work, but you don't finish the experiment. If you're going in the right direction, you go over and you say, refine this hypothesis for me, and you go around it. This is how acceleration happens in science from data. So we're moving from model-driven, top-down. This is the way science occurred. I guess this is kind of a complicated slide. I think I'll skip it. But I will tell you that I think I'll move on. That's a complicated thing about economics. Economists are just beginning to use big data. And governments have recommended that economists do not use it yet, because if you make an error in an economic model, it could have an impact on the stock market or on the economy of a country. So I think that's a warning that people with a good understanding of statistics and economics understand you have to be very careful in applying big data analytics because you can make errors. So economists tend not to use big data yet. It's just beginning. So to conclude this section on big data and analytics, big data and analytics was a big hype over the past 4 or 5 years. The hype is tuning down a little bit because people are having difficulty applying it. It's very successful in some areas, but the reality is it is more important than this. The Gartner hype cycle says it's decreasing in importance or interest. I would say that the future of good medicine is going to come out of big data. And so it's very, very important. But it's in its infancy and it's very hard. And I don't know if you recall what was called the AI winter. It was a period where people believed that AI was going to solve a lot of problems, and it didn't. And so they lost their funding. It was called the AI winter. And the same thing may happen with big data. It's made big promises, and if it doesn't deliver, people will think it's unimportant. Okay, so now what I'm going to do, you'll have to tell me how much time do we have? Would you?
We'll have to finish about 6.
Okay.
So it's about half an hour.
So now I want to give you my view of big data. So I've spent 3 years looking at very large use cases, and I'll share one of the use cases with you to give you an understanding of the way I see big data. And I don't mean the way it's applied in marketing and many other areas. In fact, the vast majority of big data applications happen in areas where errors don't make as much impact as they would in medicine, and someone might die. And there's a good reason for that. So one of the most famous statisticians and experts in data analytics, his name is Michael Jordan from the University of California, Berkeley. He was asked in an interview a year ago, what's the really cool thing in big data? And he answered, Big data itself is not important. You need to know, oh, you can't see the colors here. You need to know the entire end-to-end ecosystem, the entire work that you do from finding the data all the way through the analysis. So that's what I'm going to share with you here. Data analysis, or data science as it's often called, appears to be you have data in a model, you apply some analytical methods, and you get a result. And you just do this again and again and again. That's true. I believe that to be true, that the models could be economics, they could be particle physics, it could be genetics, it could be all sorts of things. And you do different kinds of analyses and you get results. So that's what analytics is about. And I call that data intensive analysis, and many people call it data science. What I want to share with you is that's only 20% of what people do with big data. The other 80%, and 80% is the amount of time they spend, the amount of work they spend, the amount of money they spend, is getting data from where you have to find it, curate it, and make it ready to go into these data. Data doesn't come from nowhere, it comes from somewhere. And there are two steps in getting the data. First of all, you have to discover it. So you take raw data and you put it into a big repository. Some people call it a data lake. The second so now that the data is all there, a scientist comes, so let's say that this is all the kinases, information on all the p53 kinases. That's in a database. Then a doctor comes along and says, I want to study a particular kinases under particular conditions. So you do an analytical data acquisition. That is, you take a subset of this data that is related to their analysis, and then you do the analysis. This is the big picture, and this is what I call data science. Because if you make a mistake anywhere along here, you make a mistake at the end. So data science is the entire scope of, covers the entire scope from finding the data to producing the results. Now, this is the flow chart that came from the IBM research that found the 2 cancer drugs. And just, you start at the bottom with raw data. So I'm just putting my own terminology on top of it. You start with the raw data. You create a model, they call it a graph model of kinases, and then you analyze it. So I'm just trying to show you that the methodology used by IBM has those 3 steps. Getting the raw data, creating a model of the data, and then doing the analysis. This took 3 years, this took 3 weeks. How about that? Setting it all up in Watson took about 3 years, doing the analysis, figuring out what data was useful. Once the analysis was all set up, the actual discovery of the kinases happened in 3 weeks. So now Watson is set up for kinases and other diseases, so this rapid acceleration of discovery of medical cures is going to go very, very fast. So now I'm going to get to data science and tell you a little bit about it. If you look in Wikipedia, it says extracting knowledge from data. Well, sure, it's like going to a bank, getting money, go to a bank and take a lot of money out. Simple, right? Well, life's a little bit more complicated. You don't just go to a bank and take money. You have to get your money and you have to take it out of your account. So the same with data and knowledge. So I actually say that data-intensive discovery is using big data to do these scientific discovery things, these things we've always done in science. You want to investigate some phenomenon, cancer, marketing, economics, particle physics. So you want to examine a phenomenon, and you have to acquire new knowledge. So if I want to study kinases, I don't start with no knowledge of cancer and oncology. I've got 100 years of that knowledge. I want to get data and map it to that knowledge. So you want to get new knowledge. So who was the person who's doing data integration? Was that someone back here? So yeah, so this, we don't get away with no data integration. We have to do data integration. It's extremely hard. And you don't do big data analytics by not, you have to integrate data. It's a very hard thing to do. And you have to do that before you can do the analysis. So we have to acquire new knowledge, correct it, and integrate it together with the knowledge you already have. So data discovery is using big data to analyze phenomena, but doing all the normal things is creating models and use. So, and by the way, I prefer, so big data, maybe the term is not so meaningful. I want to use evidence. Isn't that what we do in science and in law and other places? So data-intensive analysis is a process of analyzing big data with analytical methods. It's very simple. I have model, so I've got all the data there, but I need a model. For example, in CERN, when you look at particle physics, you don't just look at random data. You look at data that is framed within the standard model of physics. That's the model. And what methods do you use? Regression analysis, machine learning, thousands of methods. And so a process is the process of getting data, doing the getting data, cleaning data, the entire workflow. Okay, so now I want to put big data in the context of data, all data. So 98% of data analysis in the world is done in Excel. This isn't big data at all. That's 98%. It's what we've known for years and years. Only 2% of data is over massive amounts of data. Very few people have massive amounts of data or the machinery to do it. Of the 2%, 96%, and that's my personal estimate, is extremely simple stuff. And I don't mean to be rude about marketing, but you can understand that marketing models of customers, I mean, I don't understand marketing, but you can understand that's much simpler than particle physics or genetics. So I'm at the big end of really complicated models. Happily, big data works very well with simple models, and one of the leading data scientists, he's at Johns Hopkins University, he says, if your model isn't simple, you're probably doing it wrong. And he means not people doing particle physics or genetics, he means people using big data to do analyses in domains that are much simpler than particle physics or cosmology or something like that. So the typical things where the models are simpler and therefore errors are not as likely are customer analysis, so that's what you were talking about. These are the areas where it's been used. How your company operates, looking for credit card fraud, and looking for how to design a new product to meet customer needs. Those are, and then another sequence of things is impacting customer relationships. So these are the ones that traditionally have been, over the past 5 years, have been successful. I'm not talking about those at all, because I'm interested in really big ones, complex data analysis. Why? Am I doing this to impress you? No. Well, maybe. I'm doing this because I want to look at problems where the machinery breaks, to find out why it breaks, to find the mathematics that allow it to not break. So I'm not interested in the ones where the models are simple and they probably work perfectly well. I'm looking at the bigger ones, and you know what happens is when you get a new understanding and you come back to a smaller case, you will be able to improve the smaller, simpler cases as well. You can't see this very well in this diagram, but most, like Tableau, if you use Tableau or R or some of these other tools for data analysis, they tend to be click and point. That is very easy to use. You use this algorithm on that data. Very often the tool finds the data for you. I don't know how they do that, but they do. This is a modest size workflow in science. The reason I'm showing you is you can see that in most of science and engineering, very complicated steps. So it's not simple at all. And now I'm going to tell you a use case which I found very exciting. And it has to do with particle physics at CERN in Switzerland. So I'm sure you probably know there's the linear accelerator in Switzerland, the Large Hadron Collider. There are each project, so ATLAS is a project, CMS, ALICE. There are actually 7 projects, but the biggest ones are ATLAS, CMS, and ALICE. And the Higgs boson was done by ATLAS and CMS. Let me tell you, and this has to do with statistics as well. The Higgs, everybody has heard about the Higgs boson? It was discovered it was announced on June the 4th, 2012. And it was discovered by 2 teams, the ATLAS team and the CMS team. When you have a $10 billion experimental facility and only one team discovers something, how do you know it's true? So any experiment that takes place here in CERN, you have to have 2 experiments and they have to never talk to each other. They have to work completely independently so they don't bias their work, and they come up with completely separate results. And on June the 4th, 2012, the 2 teams had never shared results, and then there was a worldwide press, what do you call it? A presentation of the material from Geneva. And one of the teams was 0.49. You have to make 0.5, whatever, 5 sigma, in order to get a result in physics, particle physics. CMS got 0.5, ATLAS got 0.49. But they both were strong enough that the world agreed that they had found it. In particle physics, in the LHC, you send 2 proton beams in opposite directions at the speed of light. And when 2 protons meet, the particles decay, and this sort of simulates the decay of the particles. So if you follow the press, you think, wow, the Higgs boson was discovered like almost overnight. It only took a month or 2. The Higgs boson took 40 years. Peter Higgs and 3 other scientists speculated the existence of the Higgs boson in about 1967. And it took many years to develop the theory. The theory says that if there is a Higgs boson, when the energy level of the proton-proton interaction occurs, it'll decompose into a bunch of other things. You'll see all of these things. So when you look in the data, you'll never see the Higgs boson because it's so transient, but you'll see all of these other things. So you have to collect the data and look for evidence. It's like DNA, or it's like if there's a thief and he leaves his wallet where he killed somebody, a murderer, and he left his wallet, then you open the wallet and say, oh, it was this guy. So this is the evidence that there was a Higgs boson, and particle physicists around the world said, okay, if you can prove that these things are observed, then we agree that there was a Higgs boson. So let me tell you the workflow. How do you get there? Data comes out of the accelerator into a data processor. All of these billions of things happen every nanosecond. So somehow you have to look at them and you have to reconstruct the event. That is, at this point in time, this billion activities occurred, and then a nanosecond later, another set of, because those decays happen in sequence. Something decays into something else. So you get the data, and then you have to reconstruct what really happened in the data set. And this goes into a data set, and it goes into a database where they do the analysis. Why am I telling you this? If you're going to do big data analytics, you have to get the data from some source. You have to do a lot of processing to get the data ready for analysis before you do the analysis. So I'm trying to show you, and this is common over the 30 cases I've seen, is you get the data from a source. There is some very complex processing to get it ready to analyze. There's another cool thing here. There is another source of data. It's simulation. And simulation data says, under these conditions, this data is predicted by the standard model of physics. So for every data element that comes out of the activity in the experiment, you also have simulated data, and here's why. So I'm going to tell you about Claire. Okay, so the data comes from the accelerator into a big data pool. The data is then taken into different experiments. So this could be the Higgs boson, this could be top quark. There's 10,000 scientists who use this database. So everybody uses this data, and they select the data they need. So the woman I worked with, whoops, what happened to Claire? I thought it was there. Oh, here it is. Okay, so Claire was the person I worked with who did a PhD at CERN looking for top quark. It's another particle. So for her hypothesis over here, she was told what hypothesis to use, because these hypotheses about particle physics have been developed by the community over time. You don't just say, hey, I wonder what's there. So she was given a hypothesis. She was also given a model, the standard model of physics, but for top quark. She had to take the model and the hypothesis, and she formulated it for her particular PhD thesis, what she was studying. She then asked for data from here to populate her model, and she wrote a program to analyze the data that she acquired. Now there's a trick. This goes back to the first slide when I said a database person did an analysis of data, and they said, here's your data, it's all ready to go. And the guy said, you're fired, you shouldn't have analyzed the data, you should have just prepared it. So the same technical principle applies here. When Claire developed her program to analyze data, she could look at real data that didn't relate to her hypothesis. But the data that related to her hypothesis, she couldn't use real data. She had to use simulated data. It took her 18 months to write the program to get it working on the simulated data, and her advisory committee was 7 people. And when she proved that the program worked, it was a C++ program, that the program worked, they said, okay, you can take the synthetic data out and put the raw data in, and then you get one chance to run your experiment. For her PhD, she could push the button once, no matter what came out. So do you know why? It's the same crazy answer I gave you on the first slide. I'll tell you, because it's a little hard. I mean, it was exciting for me to learn. There are 2 reasons, one from science and one from statistics. The reason from science is, if you run a scientific experiment with a hypothesis and it doesn't work, you say, oh no, I didn't mean that, I meant something else. You've screwed up. You made an error. Your hypothesis formulation was incorrect. So in CERN, you lose. You don't get to run it again. So that you don't bias your experiment, you have to get your hypothesis worked out, and your committee has to agree. So that's one reason she could only run it once. The other reason was, every time a scientist examines that data set, they impact the confidence level of any other subsequent analysis of the same data. It's called data reuse. So that these other 10,000 scientists were not negatively impacted, any scientist can run their experiment only one time. So I'm making a big story out of this to tell you that data science is not click and point and have some Tableau or R find some nice data for you. That may work in some areas, but in general, it doesn't work. So some lessons learned, and then I will stop. So first of all, what is data analytics? It's a piece of software. It's a piece of software that you write to evaluate a query. A hypothesis is a query, right? So it's a data-intensive workflow that is 80% data management, discovering data, curating it, cleaning it, preparing it, getting it all ready, and only 20% of it at the moment is the actual analysis. So when you read papers about somebody discovering something with data science, what they probably don't talk about is where they got the data from, how they cleaned it, how they maintained it, how they shared it, how they curated it. What we are trying to do in computer science is to switch this around. We have a company called Tamer. There are many, many companies, but I'm telling you that I have experience with one where we're doing what's called data curation at scale. We're actually using machine learning to do this stuff here. We call it machine-driven, human-guided. So to the extent the machine can make a correct analysis of the data, that is curating it and cleaning it, fine, have the machine do it. But if the machine isn't very confident, we have it go to experts, and we call it expert sourcing. So it is a piece of software, but when you construct software in the old software engineering world, you would build a piece of software like an operating system or a database system, and it would run for years. In data analytics, you're changing your program every minute, every 2 minutes. You don't run your program forever. You run your program to discover things. In business, if you write a program to discover, let's say, new customers, and it works really well, you'll run it all the time because there's always new customers coming in, new purchases being made, new trends in sales of products. So you will run some things a lot, but things like in CERN or cosmology or genetics, you only run it once, but you iterate over it a great deal. The big cases that I know, not the ones that are typically applied in business, but the big cases that I know take years, as in scientific workflows, to develop. So I think what's happening now is there is a new paradigm of computing. Because this is so powerful, I think things like databases, information retrieval, business intelligence, data management, data warehouses, all of these things are beginning to shift in this direction, where you can use big data and big data programs to discover things you never discovered before. Of course, you'll use databases to do transactions, but if you have a lot of information on customers, you would love to find more information and things you never thought of before. So the question of whether an outcome, a correlation, is correct or acceptable to your community, it varies by the topic. So in particle physics, so at one end you have correlations. The consumption of chicken and the consumption of oil, they look correlated. Oh, it's not true at all. You just dismiss it. At the other end, the Higgs boson took 40 years to develop the experiment. It took a year to do the analysis to achieve what's called 5 sigma, 5 standard deviations of confidence. They then spent another 2 years looking at the same data and increased the precision to 10 sigma 10 standard deviations. That's just never heard of in science, but they had enough data to do it. So in the scientific community, 5 standard deviations is required to say this thing happened or it didn't. In crime, when you use big data, genetics, to identify a thief or a murderer or a criminal, what is the confidence level? I don't know what the answer is, but it's not 5 sigma, it's something different. It's something like when you say that you killed somebody because your DNA was on the knife, and therefore, so it was actually you at the site, I think they tend to talk about 1 in a million. So that's 10 to the 6th. Actually, that's bigger than 5 sigma. So I think, so anyway, what I'm saying is it depends on the area that you're doing analysis in to determine what is adequate proof for the thing being correct or not. Oh, and I started off with what and why. At this end, when everything's speculative, you say, I have evidence. I know that the consumption of chicken and the consumption of oil look about the same. That's speculative. And why says, I know that the Higgs boson exists because I found all of these other decays that could only be there if there was a Higgs boson. And that's causal. You say, you know A implies B. Now there's another interesting aspect of this. There's a man by the name of Piketty. He's an economist from France. And he has used economic data from 100 years to make predictions about how people's wealth grows depending on whether they have assets like investments in the stock market or whether they get their money from labor that is working. And it was a very dramatic result. He used big data to do it. But the interesting question is, the data that was collected, let's say from 1990 to 2010, was collected with great precision and with a lot of definitions as to what the data meant. What about the data that was collected in 1910 or 1915 or 1920? They didn't have the same hypotheses, the same precision in definition of economic terms. So how do you do experimentation over data that you find on the web and you don't have the metadata? You don't know exactly what it means. You don't want to throw that data away, but you would like to use it. So I'm posing the problem here. When people advertise big data or data analytics, they say, oh, go to the web, get whatever data you want, and then come up with a conclusion. But if you don't know what the data meant or the conditions under which it was collected, it's not likely you can make a conclusion. So I use the term machine-driven and human-guided, and I would claim that you need to use people, the intelligence of human domain experts together with the data to actually make progress. So the humans can add the semantics. So some of you work in semantics. The humans can interpret the data and the machine can't. The machine doesn't know anything. It only knows patterns. Multidisciplinary. So at the beginning, I gave you a dramatic example of a data person doing what they thought was the best thing for data analysis, and the scientist saying you're fired. So multidisciplinary means no one person can probably do each of the tasks involved in a total workflow, but multidisciplinary means that the disciplines need to work together so that they don't screw up the work of the next person in the line. So big data analytics is domain specific at the moment and does require different disciplines to cooperate to solve the problems. And In most of the big cases that I looked at, big pharmaceutical companies, economics around the world, Piketty in France, CERN, where there are 10,000 scientists, the cost of collecting the data and doing the analysis is so large that you don't do it on your own. It is a really large activity. And so there are massive resources, there's a lot of shared knowledge, huge costs, and already there are about 60 large communities around the world that are beginning to use big data, and these guys have the resources to be able to use it. So big data, certainly people use it in business for marketing and all sorts of other things, and that can be used in a narrower scope. But the next generation of big data is going to be these really large groupings of the sciences. So I think, I'm just repeating what I said before there. Oh, I'm going to skip that. Let's see. Yeah, let me, skip along here to the conclusions, is that? Let me go back to this slide here. I'm going to repeat what I've said earlier, that there are professional organizations who have recommended to the people who practice their work to be very careful and not use big data. So have you heard of the OECD, the Organization of Economic, OECD, the Organization of Economic Countries and something or other. They're an international organization that guides economics and statistics. And they have put out a document warning countries, the statistical bureaus of countries, not to use big data unless you really understand it. The reason is that when a country like Russia or Canada or United States puts out economic statistics from their Census Bureau, they say, or the Census Bureau or manufacturing, they say, we are producing this many tractors this year. We expect there will be a growth of this much, so by this year we'll be producing these extra tractors. There are standard economic means to make those estimates and the predictions. Now the statistician says, wow, we know a lot more information that we can ask farmers and we can ask these other people and we can enrich our data. So we may be able to give a more interesting result in predicting how many tractors we're going to produce. The problem is that the OECD, the statisticians realize the possibility of making an error is really huge because statisticians don't yet know how to use big data. And if you change your economic projections based on big data, it has an impact on countries' economies, the way an industry will work, and perhaps the stock market. So professional organizations are saying be very cautious about how you use data analytics. So let me just conclude. So what I've tried out, okay, the biggest thing that's happened in the past 15 or 20 years is the world is putting much greater value on data. You hear it everywhere, everybody talking about data. And the idea is that data is valuable to do analysis of various kinds. But the reasoning and the problem-solving techniques are not the things we used to do with Excel. They're something new. So you can do the Excel kind of analysis with much more data, so that could be better, but you can do things qualitatively different. That's what the paradigm shift is. So I'm going to say that data analysis is in its infancy. We don't yet understand it. Remember the example I said where humans understand about 7 to 10 ideas at a time? And deep deep learning and other machine learning algorithms, they look at 1 billion variables. A human being could not possibly understand what that algorithm does, let alone prove it correct. So we have a need for the data science that I am pursuing, which is, can you estimate the probability of an outcome being true in the real world? And that's important when you act on the result and it has an impact in the real world, like a medical treatment, a drug, making an economic prediction, when computers choose what jobs people get or what government benefits they get, we better make sure that those things are correct. So, that's a lot of material, but
Okay, probably we'll have time for several questions. Please.
someone has to start. Yes. Yeah.
So what did exactly happen to Claire's PhD?
Who?
Did she receive it?
Yeah, she did. But two things. One of the things, this question is a really good question, because if you're a real scientist, you have a hypothesis about some phenomenon in the world, and when you run an experiment and prove it right or wrong, both of them are results. In many sciences, like computer science, if it doesn't work out, you fail. But in particle physics, you win either way. And because when her advisory team said, you are approved to go ahead, that's almost like you now have your PhD. So she earned her PhD by spending many years, but the 2 years in which she did the top quark experiment, she had to develop her model, develop her hypotheses, do the analysis, get the results with the simulated data. And it's like the icing on the cake, we say in English. It's the cherry on the sundae that it actually worked, and she actually got a positive outcome. But in CERN and in other branches of science, when you get a negative outcome, you should be able to get your PhD as well. You shouldn't have gotten that far forward. Anyway, she got her PhD. By the way, there are no jobs in particle physics. So now she's working as a computer scientist in our company.
Okay, some other questions besides the levels of destiny?
Would be data science as a dedicated academic program? And if it could, if yes, which topic should be covered in this program? There exist some programs, but they are completely different.
Right. Right. So let me repeat your question, if I can, to make sure that I understood it. I think you're speculating, where does data science go? What branch is it? Is it mathematics? Is it statistics? Is it chemistry? Is it physics? What area is it? That's a great question. And if you search the web, you will find courses all over the world on data science, and they're all different, and they teach completely different things. Some people think it's Hadoop and R. Those are only tools. Okay. What is data science? I say data science. Oh, I didn't give you the definition, did I? Oh, let me find the definition. Oh.
You started to give us a definition, but...
No, the definition is here. And, the colors. Okay. This is, thank you for asking this question. I owe you some money. So, data science are principles and techniques, like the principles of mathematics, for discovering things. That's investigating phenomena, acquiring new data, integrating it. So this is the getting of the data and putting it in a model. But what I want to do, when you have a question you're asking, like what is truth? Truth is with respect to something. So you don't just ask a question of the world. You know, what is the price of General Motors tomorrow? I'm sorry, you do ask a specific question. So you want to investigate a phenomenon with respect to something, like a particular characteristic, and you want to do it with measures of correctness, completeness, and efficiency. It's a kind of a long definition. So this is a theoretical definition, and this might fall in a combination of mathematics, including statistics, computer science, because there's a computing component. A statistician couldn't do it on his own. A computer scientist couldn't do it without statistics. So there are various, and I think you need science, like empiricism. So there's some combination of science, mathematics, and computer science as the principles. But you won't find this definition on data science almost anywhere. Data science is defined in terms of what, why, and how. The guys who say what, he says, oh, data science is using these analytical techniques to look at data to find out this result. That's, what did I say, what? What is data science? It's using analytical techniques to get answers. That's the what. The why is, I want to discover certain patterns in data, and therefore I'm using data science. And the how is, first I do this, then I do this, then I do this, then I do this. So most definitions of data science is how you do economic modeling, how you do gene analysis, how you do text analysis, and they tend to be in local groups. And I think there's a general principle like this. So another way to answer the question according to the lecture is the scientific method developed over 400 years. We're only 10 years into data science. So it's going to emerge everywhere. Not a very good answer?
Does it mean that data science has dedicated academic program?
Data science programs tend to come out of computer science. At MIT, at Berkeley. I don't know if Stanford has a program. They probably do. But these are, in Johns Hopkins, it comes out of biology. That's where Jeff Leake is, and I quoted him earlier. So, you know, computer science started in the 50s out of engineering and mathematics. Now it's computer science on its own. And I suspect that data science, let's say in a university in Philadelphia, would come out of physics, where physicists started using it. And then as biology in Johns Hopkins, it's statistics and computer science at Berkeley, because it was a combination of statisticians and computer science in the AMP lab that started doing it. They got a funding from the US government. So it depends on the history, and because the history is so diverse, this proves that data science isn't a discipline yet. That's a good question. That's a bad answer. Still. Yeah?
I want to ask a question about data reuse. Well, I understand when we reprocess data and use it to prove some hypothesis, the results degrade. Well, because our data do not represent real world, but some preprocessed storage state.
I don't think so. Let's assume that the data is real. It represents the real world. I think that's a... I'm sorry, you continue your question.
I'm just wondering, you said that any experiment run on data will degrade...
Subsequent.
Subsequent.
Right, right.
Why? I understand the subsequent experiment is performed by the same scientist and scientist.
Different scientists.
Why different scientists? They use the same...
Okay, so...
Is this...
Okay, this gentleman is asking... At the beginning, I posed you a question. I said, gee, I'm going to prepare data for you. So I'm going to analyze it and curate it, and I'm going to get all the metadata. I'm going to tell you whether it's sparse or dense and what the distribution of data is, so I can help you understand it. But that was the bad thing to do. And so everybody says, including me, said, why is that? And then Claire got to run her experiment only once, so she wouldn't perturb the data for people later. So this gentleman is saying, why is this? It's a result from statistics, and I'm not a statistician, so I can't give you the formal answer, but I can give you an intuitive answer. And an intuitive answer is a data set has a finite amount of information. And if I go in and take out some information, it's no longer a surprise, it's known. So you have to think it's not in the data set. And then I go and take another piece of information out, and it's no longer in the data set because I know it. I don't speculate. It's not probable or not probable, it's definite. So every time I inspect the data set, it changes the content of the information in it. The more and more I inspect it, eventually it'll be exhausted and it can't prove anything that I don't already know. This isn't an easy idea, but I can tell you a story about it. Has anybody ever heard of the Hawking, what's it called? The Hawking, you know Stephen Hawking, who is the cosmologist? And you know, he did his PhD on black holes. And so the problem that was posed 40 years ago, I have a slide on it actually. The problem that he posed 40 years ago with his PhD thesis was that you can't measure black holes because even light, when it gets to the black hole, goes over what's called the event horizon and you can never see it. So you can never measure a black hole. Now, if a planet or a body goes near a black hole, it gets sucked in, and black holes over time degenerate, and then they finally explode and vanish. So the Hawking paradox, I think that's what it's called, the Hawking paradox is a body in space that has information in it, and it goes into the black hole and then disappears. And the belief is you can never destroy information. And this Hawking paradox was, what happens to the information that gets lost in a black hole? For 40 years, there was no answer. He gave an answer in June this year at a conference in Sweden called the Hawking Paradox Conference. And here's his answer. As the object goes into the black hole, it sheds its information and leaves the information outside. So you see how that relates to the question? It's very similar to why Claire ran it only once. Information is never lost. And so if I have data that has never been inspected, it's pure hypothesis. And when I go and take some out, I prove that it's wrong or right, either way. That data is no longer in the hypothetical arena, it's now concrete. So every piece of data I inspect, it becomes concrete. And that means that I've tried my hypothesis, and Sergey can never try my hypothesis or anything around it again. It's already known. And so, and I would also say that when you know something, there's no absolute truth. It is, you know it in a context. So let's say I have a hypothesis and I make data that has never been seen before concrete, but I interpret it blue and I should have been red. Sergey may come along and say, I actually think it was red. There's no way he can test because I've made it blue. What I'm saying is, when you make data concrete, you may also add information to it, enrich it, and interpret it. The interpretation may be wrong, but you can no longer examine it anymore because you've made it concrete. I guess that's really hard. It's a difficult topic. But I hope you realize that there are these difficult ideas that underlie the analysis of data. So you need to understand statistics. And maybe, so the example I always use is producing strawberry popsicles. Does everybody know what a popsicle is? It's a candy. So producing candy on your manufacturing line. And you say, in the summer, when it's very hot, what flavor should I produce? And you use big data to determine it. You have to tell the production line with enough advance notice so that they can change the resources to produce the strawberry popsicle. And if I'm wrong, then you don't sell the popsicles and you lose all the investment. So you need the information in advance, but you can be wrong. So you want to make it correct. Okay, that's a long answer to a question, but it's a very hard question. Very hard question. I'm not sure I understand it. Okay?
I hope that thanks to this talk, our understanding of data science improved significantly. So thank Michael again.
Thank you. Thanks for coming. Thank you.